So this is about a paper that came out a couple of weeks ago. I forgot to write down the number, with Jackson Fliss, Alex Frankel, and Sean Hartnell. In particular, you might have noticed that there was a list of references in Shumit's talk where Alex's name was everywhere, and he's applying this year, so hire him, please. Okay, now to get into the content. So let me remind you, so one of the most interesting facts about ADS-CFT is the RT formula, the Ryu-Takayanagi formula, okay, which says that if you have a CFT and if you have a subregion B in the CFT, okay, its entanglement is given by the area of the minimal surface, okay, with the homologous to the actual region. In particular, the region little b between the minimal surface and the boundary is encoded in that boundary subregion. Okay. So now this one aspect of this, I think, which is not explored as much in the literature, which is the following: gravity is a theory which has diffeomorphism as a gauge invariance. Okay. So it's hard to define subsystems in the bulk. This guy gets around that in a very, very clever way. It says you don't get to pick the subregion. You only get to pick its gauge invariant part, which is the boundary projection. And then the theory picks the subregion for you. Okay? And in fact, to toot my own horn a little bit, I wrote a paper in March this year where I kind of made this precise, that there is a connection between the extremality condition and diffeomorphism invariance. Now, a very important thing people have been trying over the years is to give a Hamiltonian understanding of this formula. The proof of it is purely from a path-integral perspective. So there have been, I'm going to talk about 3 different attempts. The first one is Strominger-Waffa, okay, which took a special case, some maximally supersymmetric extremal black hole. Ashok touched upon it today, and got the area from combinatorics. This is important because it is an entropy. You want a state counting interpretation. You count states using combinatorial formulas. The second one, the second one is via edge modes. And the names associated to this, I think, in the context of gravity, it was first explored by Karlip in 1995, and there's been a modern explosion starting with Donnelly and Friedel. Other names who have done important work are Ciambelli, Ley, Pai, Anthony Speranza, and Syed Farouk Musawian. Okay. What it says is that, okay, let's look at little b again. In the phase space of little b, there are diffeos that are supported on capital X on the boundary of little b. Okay, and these diffeos have to be entangled with analogous diffeos from B bar, from the complementary region. Okay, these are called edge modes because they live on the edge. And people have studied these edge modes in quite some detail now. And one thing they find is that there is some algebra, and there's a phase space, there's some modes in a phase space, there's a Poisson bracket algebra, and some areas like a Casimir. Okay. There's one, but you can't really go from here to having an entropic interpretation. That is something that is lacking. The third thing is the random tensor network literature, okay, which gives the min, which is neither of these 2 guys give the min. Okay, what it says is that you think of the boundary state as being created by some quantum circuit made out of random gates. These are called tensor networks. And then your discretized discretized boundary subregion is something like this, and then you minimize over various different cuts of this quantum circle. Okay? Yeah, QI people don't get angry at me for calling something without unitary things a circuit. But this is also a sort of Hamiltonian approach to trying and understanding the RT formula. And this does not have gravity. It is purely a toy model, but it tells you something about where the min comes from. Okay? This does not have entropy. And this does not have a horizon. It really works in a regime without a horizon. So it's important to put all of these things together. I won't do it. So let me say what I will do. We'll take a simple model of matrix quantum mechanics, okay, which Shumit helpfully introduced for us, which does not have gravity, but does have diff invariance. Okay, in particular, it will have something called volume preserving diff invariance. Okay, what this volume preserving means for us is that the volume of a subregion is gauge invariant data. Similarly to how the boundary projection in ADS-CFT was gauge invariant data. In this, we'll define a relational partition of degrees of freedom, of color degrees of freedom. I won't actually have time today to talk about why the partition is relational, but some introduction to relational observables were done by Alok and Suvrat last week, and also they turned up in Shumit's talk. Okay. Yeah. Sorry, yeah. So that the entanglement entropy given a fixed volume is the minimum over subregions wall of sigma with fixed volume of the area of sigma with some stuff and other stuff. But this is an area, the area is the leading thing. Okay. Finally, we will incorporate insights from all three of these things. Yeah.
This is the entanglement you would like to associate with V?
No, we argue that we actually get the entanglement entropy to be this.
I see. So you can argue that it is entangled.
Yeah. Finally, we use all three of these insights. We get the area from the combinatorics of edge modes. EMs are edge modes. Okay? And we get the min from something called wiggle modes, which are also part of the gauge symmetry of the theory. Okay? Which has not been seen in this literature except for one example, which I will mention in the end, and was actually the inspiration for this work. So that is the main result of our work. So now let me introduce them.
This is the volume of what?
Of the enclosed subregion. So we won't have a boundary in our theory. So the gauge invariant data of a subregion is its volume.
Ronak?
Yeah?
I'm a little confused. If you're saying that you're going to be looking at the minimum area bounding a fixed volume region, isn't that always a sphere? If I specify a volume and I'm in a flat...
Depends on the geometry, right?
Okay, so there's going to be some dynamical geometry?
Yeah, well, we will work in a simple example where it is a sphere.
Okay.
But the point is that our arguments should generalize beyond a simple example.
Okay, maybe I'll ask more at the end after
Yeah,
this.
yeah. Okay. But it's also important that, our arguments don't generalize, I think, to BFS as very cleanly, where one might expect something more interesting. Okay. So let me talk about the model. It's a model of matrix quantum mechanics. There are three Hermitian matrices, okay, which are n times n matrices, and n goes to infinity. Everything is, n will be the largest parameter in the game. Lagrangian looks like trace x dot squared plus v of x, where the square assumes also a sum over a. And Lagrangians like this have a un gauge symmetry. Which takes xa to u xa u dagger. Okay, which again Shumit introduced us to.
You're not doing the gauge theory?
This is the gauge theory. I didn't write the potential. Yeah, but yeah, this is a gauge symmetry. Okay. The particular potential we care about looks something like, my entire talk is up to factors. Something like this. Okay. This is a very strange potential to write down, but the reason is that it has a very nice classical minimum. A way to make a classical minimum is to send the potential to 0 and x dot to 0. Right? So it's a static solution. And there is, to make the potential 0, we need this. Okay? And you've all seen this. This is the SU2 algebra up to a scaling, which is this new parameter. Okay, so you get the classical solution. I'll write this as x classical A is equal to nu times JA, where this is the n-dimensional generator of SU2. Okay. Further, you know there's something nice about SU2. There's a quadratic Casimir. Okay, and this is the fixed irrep of SU2. So that means that this guy is nu squared n squared. This is another equation you've all seen before. It is the equation for a sphere in 3D space. Can I write here? Is that visible? Yeah, okay. So you get something like a sphere. There's an emergent space in the way that Shumit actually outlined for us, which is a sphere. In fact, it's a fuzzy sphere. It's fuzzy in a way that has nothing to do with quantum mechanics. It's fuzzy because the coordinates are matrices. Okay? Yeah. So now, let me remind you again about something. J3 in the n-dimensional irrep looks like n, n minus 1, 1 minus n, minus n. Right? This is the J3 generator always looks like a diagonal matrix. So you can think of each of these eigenvalues as kind of a latitude of the sphere, where this is the x3 direction. Okay, I'm being very heuristic here. Oh, this is, like J3 is like J3 acting on Jm is equal to M Jm. Yeah. Yeah. So anyway, the point is that the x1 and x2 coordinates don't commute with x3, so you can't localize it at a point in the three-dimensional space. You end up localizing it on a circle. Okay, again, I'm being very heuristic because this is not the main point of the talk. I just want to illustrate something important. Now, you remember that there is nothing special about this basis. You can do a gauge transformation. Why not work in a basis where some u x3 u dagger is diagonal and ordered? See, here J3 was diagonal and it was ordered. It's in decreasing order. And that fixes the UN gauge symmetry. If you make this a gauge condition, then there is basically no interesting UN gauge symmetry left. There's a U1 to the N, which Shumit mentioned, but I think that's boring. Okay. So When you do this, yeah, n is it's part of the definition of the theory, right? Yeah. You never want to be in the adjoint. You want to be larger. Yeah. That's right. Good. When you do this, now U x3 U dagger is a much weirder thing. The eigenvalues of that guy could look like this on the sphere. In fact, one eigenvalue could look like that. One eigenvalue could look like that. Okay. The point is that these unitary transformations can get really weird in geometric terms. But yes, but I'm working on a basis where I'm looking at the eigenvalues of U x3 U dagger. Where are they localized? Not U x3 U dagger. Oh, sorry. This is some matrix in UN. No, but the localization is different in the x1, x2, x3 basis, in the x1, x2, x3 emergent space. This is like, this is technically implemented by something called the Moyal map, but I'm just giving you a very, very broad picture. Yeah, the eigenvalues are the same, the numbers are the same, but the localization of the degree of freedom is not the same. Basically, because once I add quantum fluctuations, all of these things will fluctuate. And then you can ask what fluctuation of the sphere that looks like. Okay. So I'm shoving a lot of details under the rug here. Yeah. The point is, oh, you're right. Thank you. Yeah, I guess this is n by 2. Okay, whatever. Yeah, Gautam is right. Yeah. Anyway, the important point here is that the UN gauge symmetry goes to something called volume preserving. And the reason it's volume preserving is the thing Abhijit brought up, which is that the actual eigenvalues don't change. Okay? And that transforms into the fact that it's volume preserving.
This is volume preserving all the fuzzy sphere.
Yes. And I'm going to call it a diff, but actually, as I just showed you, this is not a diff. This is neither smooth nor continuous. But it's some rearrangement of space. That's what I care about. Huh? Yeah.
So it's larger, and that's why it's not n minus 1 by 2. Is that correct?
No, the answer to Gautam's question was he was right, and I just made a silly mistake.
No, I understand, but I'm saying that like it is, but it looks like it should be n minus 1 by 2 or something like that.
Yeah.
Okay, fine. One more thing. So the potential that you're taking here, wouldn't it have like smaller representations which will also be solutions?
No. See, the x's are n times n matrices.
Sure.
Yeah. The fact that it's also an n-dimensional irrep of SU2 is something that pops out.
So if, for instance, x equal to 0 will also be a solution. Right?
Yes. That's true.
Yeah. So
I didn't say this.
Wouldn't it be like some instability, something like that?
This in the quantum theory, this is a metastable solution. Yeah.
But I also suspect this potential is actually this is the same thing that is there in the BMN.
Oh yeah, sorry. This is called the mini BMN model. I should have said that.
Okay. So in the BMN model, will it be stable?
Yes, because of the fermions.
Okay.
Which I have thrown away.
Thanks.
Yeah. Thank you for that. Now. Oh yeah, let me just say one more thing on that side of the board. I apologize to whoever is following me, which is now we can look at a quantum eigenstate. Okay, I'm not saying ground state. It's just some eigenstate, which looks like a Gaussian wave function with the peak being xa equals x classical A. and there are quantum fluctuations. And the size of these quantum fluctuations is like roughly 1 over square root nu. Okay? Of the Hamiltonian. Yeah. Okay. The width of this structure of this Gaussian is like 1 by square root nu. So in the limit, n is much greater than nu is much greater than 1. This is reliably a fuzzy sphere. Quantum fluctuations don't make it into a ball. Okay, whereas in the 't Hooft limit, it becomes a ball. So we will work in that limit, where you have reliably a fuzzy sphere. Okay. Now we get to the part about partitions and let me talk about the Hilbert space for a minute. So this is a gauge theory. The physical Hilbert space is a bit hard to write down. So first we usually write down something called the extended Hilbert space, okay, which is given by all functions of Hermitian matrices. Okay, which we can also write as span of kets, each ket corresponding to a Hermitian matrix, the 3 Hermitian matrices. And then there is some operator that implements gauge transformations, which takes this guy to that guy. Okay? So this is not the physical Hilbert space. This contains many copies of HFIS. Okay? It is called, it contains many copies of HFIS. So one example is, you take the subspace H invariant, where this pi hat of U acts as the identity operator. Okay? Which basically means you take X-ray and integrate it over the entire gauge orbit. But then this need not be the only one. H invariant is normalizable because it's a compact group, but I'm going to introduce non-normalizable ones now. But you're right, I'm going to not be careful about normalization. We have footnotes about that. Okay. So as a toy model, think of Hx as R2 and think of gauge transformations as rotations. Okay. So then a gauge orbit looks like a circle, and H invariant looks like taking a sum over all vectors around the circle, a superposition over. Okay. But there is, for example, you could take this vector. Okay. All vectors along this direction. That is also a representative of H fields in the full Hilbert space. This is a gauge fixed representation. Or you could like do something much crazier. You could integrate over this part and that part and that part. That is also a representative of H fields. The reason is, in this model, the gauge invariant data is the radius, and no matter how you integrate over the sphere, the radius doesn't change. So you can always read off the radius. Similarly, mutatis mutandis, it all works in this complicated case. Okay? Yeah, so, but actually it's quite important, like different ways of, these different representatives play a role in what I'm going to say now. Okay? So now we will use these points to define partitions. So in the paper, we did two things with defining partitions. One was what I'm going to tell you now, which is just like a sort of prescription. You have to take my word for it. The second was we justified that prescription in the language of relational observables and internal quantum reference frames. I don't have time to tell you about these, but I did see that there's a bunch of people from Philip Hohen's group, and I saw posters from Biljana Tomova, Julian de Wuist, and Stefan Eccles, and they all know everything about quantum reference frames. Please ask them questions, not me. Okay. So, how do we define partitions? First thing you notice is that Hx has a tensor product structure. In the matrix, in Hx, each matrix element is a free particle, is some particle. Okay? So I can split up the matrix, call this in, and then I have some Hilbert space corresponding to that block. Okay? I'm being a lot more low-tech than Shumit was. One reason I'm being a lot more low-tech is that he had to worry about fluctuations in the size of this block. I don't want to worry about that. Okay, that's going to be an uninteresting contribution from my point of view. So I want to throw that away. So I'm going to take a fixed size block, which is an M. Okay. So we will use this. So our algorithm will be pick a representative H phase in Hx, okay, and different choice of representatives along with this tensor product structure will give you different choices of subsystem. Okay, different choices of subsystem. Okay, so let me explain that a little more. Okay, so there are two parts of the gauge symmetry, of the UN gauge symmetry. One is what I'll call UM cross UN minus M, and one is the flag manifold, which is UM cross UN minus M, quotiented out of UN. This is a left quotient, and it turns out to be incredibly important that's left quotient and not a right quotient for reasons I won't bother you with. Okay, these things are called generalized flag manifolds, so that's why F. So, how does the UM cross UN minus M act? You split it up. It kind of mixes stuff up here. It mixes stuff up here. Mixes stuff up here. Mixes stuff up here. Does not mix the four blocks with each other. Okay. I will throw an equation at you now. So let's call this x sigma sigma, x sigma bar, x sigma bar, sigma bar. Okay. So, and if you call the UM matrix UM and this guy U tilde, x sigma sigma goes to U, x sigma sigma U dagger, x sigma sigma bar goes to U, so this is UM, U tilde dagger, and the x sigma bar goes to just gets conjugated by U tilde. Okay. So now notice something. I want to call this block in. So all three of these blocks are out. So this UN minus M acts on only the out degrees of freedom. Okay, so it's boring. Doesn't do anything interesting. UM does something incredibly interesting. It acts on both the in and the out degrees of freedom without mixing them up. Okay, and if you remember my introduction, these are exactly the things I called edge modes. Okay, so yeah. Secondly, yeah, it acts on these three blocks. These three blocks. Yeah. Yes, but UM acts on both sides. UM acts on both this UM acts on these three blocks. Okay, yeah. Yeah. Yes. Okay. Let me draw a little picture for you.
And U tilde was what?
It's the it's the part of UN minus M. The little picture is, suppose you started in the gauge, you started in the gauge where that block corresponds to the spherical cap out here. Okay, this is the original J3 being a diagonal gauge. And then the U of M transmission. So the off diagonal block kind of looks like little strings that go between the two sides. The U of M transmission rearranges the inside. So it acts on this end of the string and it acts on the inside. So what the actual D branes inside are the left top block and the strings are the off diagonal block. Okay. So these strings are really the edge bolts for us. They are the things that are acted on by this UM. Secondly, there's the other type of gauge transformation which does this. Okay, I will redraw this. It mixes, the other type of gauge transformation mixes the inside and the outside. So it takes this subsystem and gives you something like this, with the only restriction being that the volume hasn't changed. Okay, you can get much, much weirder. I am limited by my human imagination here. Yeah, exactly. The topology can change. Okay, we call these wiggle modes for the obvious reason that they wiggle the region. Yeah. Yeah, this has actually become, in the last 2 minutes of my talk, I will talk about that. Sorry guys, be louder. The difference is that the UM acts on only the inside of a spherical cap. Okay, it moves the strings that cross the boundary, but does not move the boundary. This guy just moves the boundary. Okay, in terms of the matrix, UM does not mix the different blocks with each other. It leaves the degrees of freedom in the right block. These other guys just move the block around. Yeah, just it's the quotient of UN by this UM cross UN minus. Yeah, it's formal like. Huh? Yeah, the flag manifold is the wiggle mode. Thank you.
Precisely because of the existence of these modes, your choice of subsystem is not giving it. It depends on, I choose it in some frame with some value.
That's why we had to use the relational language. Yeah. Which unfortunately I won't get to, but yeah, I can tell you offline more about it. Okay. So now, let me tell you what Frankel and Hartnoll did, following Schmidt and friends, and also Hampapura, Harper, and Lawrence. It's a bit of a tongue twister. Okay, they took, they took a representative. Of the state in Hx, where F tilde was gauge fixed. But UM cross UN minus M was integrated over. Okay, so the state is annihilated by the UM generators. Okay, but again, as I told you, UM generators act on both the inside and the outside separately. So the inside can transform non-trivially, the outside can transform non-trivially. It's only the fusion of these two that has to transform trivially under UFM. What this means, F tilde is the flag manifold, the quotient which is just very long to write. Okay, thank you. What this means is that your state, okay, let me call this psi fh because I'm just telling you what's in the paper. You sum over irreps of UM Okay. Some details. This is the probability of finding the irrep. This is a singlet state that does not transform under but depends on the irrep. Times the interesting part. D mu is the dimension of the irrep. Okay, so the state very generally looks like this. This is something that, for example, Sandip and I worked on in 10 years ago now, almost. Yeah. What this is saying is that the inside and the outside are in non-trivial irreps of UM, but together they are in a trivial irrep. And this gives you an entanglement entropy, which is like log d mu. More precisely, you get sum over mu, p mu log d mu. You get the average log dimension of the irrep as a contribution from here. You also get contributions from here, but I'm throwing those away. Yeah.
And you always get this.
Yeah, because it's this is a representative for the physical state.
I know, but so let me take. I can take any state. I can take an eigenstate for instance.
Yeah.
I would only have one.
A physical state.
I know. First, let me start with hx. I take an eigenstate, and then let me average it over you to get a physical state.
Yeah.
And you're saying you'll always get this universal one.
Yes. Yeah. Yeah, that's right. Yeah. You'll get the universal contribution given a particular prescription, which is picking the representative that has this tensor factor in it. This is not a non-arbitrary. This is a bit of an arbitrary choice. You don't need this tensor. You don't need this tensor factor to represent the operators, but it's natural from the point of view of Hx. Maybe we can talk about this later. I shouldn't have brought this up.
Just one question. You compute the entanglement with the extended Hilbert.
Yes.
You start with.
So that is the prescription that gives you this. Yeah.
Yeah. So that's what. But then he said there's some starting.
Yeah, because deciding to compute it in the extended Hilbert space is a prescription.
So that's why you're saying it's because you choose a particular extent.
Yeah. Yes. Yeah, and there are some wonderful arguments by 5 minutes. Okay. Let me be very quick. So then Frenkel and Hartnell actually did the calculation. Okay, they did the calculation. Again, they looked at the fuzzy sphere, they looked at the spherical cap subregion, which is a particular choice of gauge in this F tilde group. Not a group, but yeah. And basically they found that there is exactly one irrep that dominates. And that irrep looks like a long Young diagram. For those of you who don't know what Young diagrams are, don't worry. This is just a picture right now. Where the length is the area of the boundary. Oh, my areas are one-dimensional and my volumes are two-dimensional. Please don't mind. Okay, so this you can actually kind of think of, this Young diagram as discretizing the boundary, like in those pictures about Bekenstein-Hawking entropy. This is the state that I just mentioned, that I explained. It's a fuzzy sphere state.
I know, but earlier you were just talking about general states in the.
Yeah,
Now
they did the computation in this particular state. Yes.
you do the computation in this state.
Yeah. Thank you.
Is this an energy? This is not an energy eigenstate.
It's an energy eigenstate. It's not the ground state, but it's an energy eigenstate.
What about the fluctuations they don't have?
No, with the fluctuations, it's an energy eigenstate. But like you can the fluctuations play a role in certain terms. They're negligible. Yeah, this is a leading order statement in N and nu. No, it's metastable because the ground state is at x equals 0.
In large N, because if the potential term dominates and you take small with the boundary, there's some fluctuation.
Yeah, so like the true ground state is around x equals 0.
Classical potential is 0. Presumably there's only one.
The contribution minimizes the classical potential.
Yeah.
If it's close to classical, it's some necessary.
I'm running out of time and I have a couple more things to say. I'm sorry. Okay. Anyway, it turns out that it's dominated by the single irrep at leading order, and the entropy that you get from that term, the log of irrep term, is literally just area log area. Okay, and this area actually has a 1 over G Maxwell in it. So the EFT in this theory is not gravity but Maxwell theory. So you get 1 over that coupling constant. Area is the length of this boundary. Yeah, but that's also equal to the, in the Moyal map, the length of the boundary. Yeah, good. So now that is what happened before. Then we were all very annoyed about this part. So what do we do about that? Well, here's a proposal which doesn't work in an interesting way. I have 4 minutes, okay. That should be just about enough. Yeah, this was before I knew about relational, well, this is before I had incorporated relational observables deeply into my being. Yeah, now I'm not annoyed about it. But here's an alternate proposal anyway, which is to take the state which is invariant. It's summed over the entire gauge symmetry. Okay. So now what do? You still define the subsystem to be this M cross M block. Okay. This and don't worry about what it means. Just do a calculation. You know. Then you realize that basically this thing is a sum over all volume traceroid maps. So there's one branch of the wave function where it looks like this. There's another branch where it looks like that, and so on. You know? And the point is, all of these have different degrees of freedom in them. So so just from within the system, you should be able to distinguish, am I in this branch, or am I in this branch, or etc., etc. You know?
The different diagrams are related by unity?
They're related by unitary in UN.
In UN?
Yeah. No, that was from the part that didn't mix the inside and the outside. The part that did not move the boundary gave that. Yeah, it came from the thing where it was gauge fixed over the flag manifold. Yeah, that's why you got to pick the region. Yeah, by the Frankel and Hartnell did it for one region. Yeah, yeah.
But they gauge fixed, but did impose Gauss law, right?
Yeah, but Gauss law for the UN, not for the full UN.
Yeah, of course.
Yes.
Yeah, of course.
Yeah. Anyway, so the point is, it should be possible to tell the difference between these different subregions from within the subregion itself. So, how do you write that down in density matrix form? What this means is that the density matrix should be approximately block diagonal, where this corresponds to this block, this corresponds to this block, and so on. Okay? So mathematically you write it like this: integral over f tilde dv rho v, where rho v is the density matrix calculated in the Frankel-Hartnell story, but for that particular subregion. Okay? Now, anyone who's looked at a random tensor network will know exactly where I'm going, but let me do this for the rest of the audience. One nice way to calculate entanglement is as 1 minus n dou by dou n log of trace of rho to the n. Okay? Evaluated at n equals 1. So we care about calculating trace rho n. We care about calculating this at n greater than 1. This condition is very necessary, and I think Pratik will talk more about it later in the week. Okay? Now you calculate trace rho to the n. This looks like integral over dv, trace rho v to the n. And this is a very, very large space. Okay? The dimension of the flag manifold goes like n squared. So, oh god, okay. So you might say, okay, I will evaluate 2 more minutes, I'm sorry. Evaluate this by saddle point. And you might say, oh, then this looks like max over V, trace rho V to the n. Okay. Then the next step is to notice that a single irrep dominates in rho V, and that after some after some work tells you that this guy looks like the entanglement entropy for the region corresponding to V. Okay, e to the minus entanglement entropy for region corresponding to V. So this max becomes a min in here because of this minus sign. And then when you do all of that, you get SE is min over V, SE of V. This is all very well and good, assuming the saddle point approximation works. Saddle point approximations don't always work, okay? Because the volume can overwhelm the saddle point. And it turns out that in what I just told you, that does happen in a very universal way that's not particularly model dependent, okay, or state dependent. So we were ready to call it a day, but then we realized that in the holographic derivation of RT, something similar should happen, because it really looks like the minimality comes from the settling down of some cosmic brane on a minimal surface. And there are all sorts of crazy fluctuations here you might have to sum over. Okay, and there's no reason to believe that the same thing won't happen there. We haven't done the calculation, but back of the envelope says it will happen there. So it seems, just a minute. It seems that we have to coarse grain the Wiggle modes, both in like expectation and gravity. Definitely we need to do it here. And when we coarse grain the Wiggle modes, we understood that in terms of an averaged internal quantum reference frame, which again, ask me offline or ask the Okinawa people. And so that's how we got the minimal area formula. So this has some just last few sentences. So the final message is we actually got a toy model for the RT formula in a very simple model from a top-down Hamiltonian perspective. Some important things to keep in mind are that you should never think about only looking for the area in Hamiltonian. You have to look for the min. And actually you have to look for the max in time-like directions, which we don't have to worry about here, but in gravity you have to worry about, and that's incredibly confusing. In particular, I wrote a paper with Aaron Wall last month, where we argued that for most surfaces, it's not area that has an entropic interpretation, but something else. It's only when this is satisfied that you get area. Okay, so that's one lesson for thinking about the RT formula. The other message I want to send you is echoing Shumit. Matrices are cool. Think about matrices. Thank you.
I kind of lost you towards the end. I'll ask you offline, but just very quickly, between what you did there and what you then did later on this side, is it that you decided to now think of the state as embedded in the bigger full UN group, including the flag group?
Yeah, we picked a different, it's the same size because it's like isomorphic to the physical Hilbert space, but like it's in the HX, it's a superposition over more stuff.
So roughly, is it that you worked in an even more extended Hilbert space and therefore got a further, contribution to edge modes in a sense?
Yeah, I think maybe you can say that. Yeah, I would think of there being one extended Hilbert space and various subspaces, one extended Hilbert space and various subspaces. But I think you can also go the other way, where you think of them as extended Hilbert spaces embedded inside extended Hilbert spaces.
Okay, thank you.
I'm a little bit confused about why these situations are this gauge fixed and this invariant. Usually we think of gauge fixing as, another way to extract the gauge invariant Hilbert space. So in particular, instead of doing invariant, I could impose an equivalence relation, right? Which is, and then this would be one representative of. So I'm confused. I mean, is this why these situations are very different? Why this?
I agree completely, and that is something that in general with like not just in gauge systems, but it's very sharp in gauge systems. There is like you have to choose a factorization map to define an entanglement entropy. Relative entropies, for example, depend only on algebras, but entanglement entropies require something more. They require embedding a physical Hilbert space into something that factorizes. This is also true without gauge theory, but very clear here. And one question is, okay, is there anything special about one of these factorization maps? Okay. And if you just look at bipartite entanglement, the answer is just no. This was argued in the paper by Longo and Witten, and then Pennington and Witten over the last couple of years. In a very nice way, because it all depends on the commutative algebra, and there are many, many different probability distributions on commutative algebras. Anyway, so that was a very broad thing. But in a paper I wrote with Chris Akers and Annie Way in April, sorry for tooting my own horn so much, but in that paper we showed one example, very, very toy example, where thinking about multipartite factorizations actually gave you a unique factorization map. Okay, so I don't know if that generalizes to any interesting cases like MQM or gravity, but I hope it does.